So what we're talking about today is radiographic technique in digital imaging. And it will, anytime we're talking about radiographic technique, we can talk about it in terms of what works for fluoroscopy and also what works for digital imaging. They're fairly interchangeable. There's some ways that fluoroscope works differently, like in terms of the way it sets MA, and the way that it has certain safety parameters in place. But for the most part, it's fairly translatable. So I'm going to be looking at the big bullet points. I'm going to try to make this as simple as possible. So I'm probably going to lecture kind of long. We'll take a break in the middle, but I'm going to try to make this as simple and as basic as possible. I might pause the lecture from time to time in order to whiteboard some about what we're talking about. Here's the learning objectives that I've identified. We're going to go back over what is subject contrast. And you're probably sick of hearing about subject contrast at this point, but without subject contrast, we wouldn't have a picture. And so understanding the things that result in a good subject contrast or a diagnostic subject contrast is very helpful. So we'll look at each level of that. We're going to talk about the effects of three different things on subject contrast, so tissue thickness, the physical density, as well as atomic number. And honestly, there's some real mysteries here in terms of how X-rays interact with matter. And honestly, recently I stumbled across an experiment with the juniors that I don't have an explanation for why the X-rays are doing this. They did it. I actually sent in photographs to the ASRT of what the X-rays were doing in terms of the resulting images. No one at the ASRT can answer my questions about it. So we'll talk about that little mystery here in just a minute. We're going to illustrate some of the effects of scatter radiation on subject contrast in the remnant beam. There's a lot of pictures in this chapter, and so it's helpful to look at those pictures and know what is he talking about in terms of the effects of scatter on our pictures. We'll talk about how KVP works and what happens as we increase KVP in terms of interactions inside the patient, as well as how digital systems can counteract that. Talk about reducing scatter production, and we'll also talk about ways to clean up scatter once it's happened. And then we'll talk finally about automatic exposure controls, which are used by both X-ray and radiation therapy for the control of technique. All right, first, subject contrast. So subject contrast, if I'm looking at this illustration here, subject contrast is everything that's going on between the patient and the image receptor. So on this illustration here, this area right here is the area where subject contrast lives. The area between the patient right here and the image receptor, patient seen in that transaxial view. So what this illustration is showing us is we've got a primary beam, right? Or an amount of radiation incident on the patient. So that's what this label right here should say is primary beam. It's exiting the X-ray tube from a focal spot, right? From a point on the anode where the X-rays are being produced, right? Some of that primary beam is striking the patient and just being absorbed, and we generally call that photoelectric absorption, right? So we'll talk about what guides that absorption. Without photoelectric effect, we would not have diagnostic X-rays. It's essential to the X-ray process, the imaging process. Some of them are just stopped, right? And then there's a small number of them that are scattered in funny directions. In fact, if this graphic was correct, the predominance of scatter would be coming off the patient in this direction. But that'd make for a pretty confusing illustration, right? But like any X-ray tech knows, strangely enough, if you're in the OR and you're working with a C-arm, one of the safest places to stand is opposite the patient, right? On the other side of the patient. Why? Because it might seem that the X-ray, you're right in the direct line of the X-rays. You're actually not. You're using the patient as a barrier. If you're standing on the side of the tube, it might seem that you're standing in a safer place, right? Like if we're at the firing range and we're all using guns, you want to stand behind wherever people are shooting, right? X-rays don't work that way. A lot of them backscatter off of the patient and could strike you as you're standing by the tube, right? So that's an important consideration, but the main reason I have this illustration here is because of this area right here between the patient and the image receptor down here. And in this area right here, subject contrast lives, right? Now, in the world of film, we could also talk about subject contrast being communicated to the latent image, what resulted on the X-ray film, right? In the world of digital, things get weird really fast, and we've pretty much already established that. Y'all have been on the brink of throwing textbooks at me for all of the weird conversations we've had to have around digital imaging. It does weird stuff. We can agree on that much, right? So we're going to say that subject contrast only lives between the patient and the image receptor, right? And to make it as simple as possible, subject contrast is simply the difference between what we had up here and what remained after the patient. It's the difference between what we had and what remained. The fancy word for that, what we have and what remained, is differential absorption. That inside the patient, different things absorbed differently, right? And that resulted in a difference between what we had in the primary beam and what remained in that secondary beam. Okay? Now, these are some terms that will be used interchangeably, and you'll notice I'm using different language to describe this, so I'm going to be really clear on the language that I'm using. Right here I've got the primary beam. It's the stuff exiting the tube incident on the patient. Down here I have the secondary beam. It's what is leaving the patient, right? And within that secondary beam is where subject contrast lives. Okay? What's happening inside the patient is the sum total of all of the photoelectric and Compton effects, right? So photoelectric, the X-rays are just absorbed. Compton, they're absorbed and scattered in a different direction. If they're scattered in a way that's not incident on the image receptor, we're going to say it's been attenuated. Something stopped it. It wasn't necessarily a helpful stopping thing, but it did stop it. So all the photon interactions inside the patient represent that absorption. And sometimes this is also called the degree of attenuation, right? So photoelectric effect and Compton effect contribute to differential absorption. Of the two, though, I've said that photoelectric effect is the better, right? Because it completely absorbs it. There's no scatter that results from photoelectric effect, right? So subject contrast, if we're going to get really fancy, we can think about it as this percentage, right? Or a divided ratio of attenuations. But that's just the fancy mathematical way of the simple thing that I was saying earlier it's the difference between what we had and what remains. So if you see that language on your registry asking you about percentages of attenuations or divided ratios, don't get freaked out. Just know it's just talking about what we had and what remained. And somewhere in there is a picture. Somewhere in there is a picture. It's a radiograph. If we didn't have that difference, we would not have an image. So you might be wondering, what are situations where we wouldn't have that difference, right? Well, an excellent example of a situation where we don't have as good of an image is actually portal imaging, right? And it's one of the reasons that portal imaging has evolved quite a bit in radiation therapy recently. What am I talking about? I'm talking about doing X-rays in the mega electron volt range, right? So for us as X-ray techs, we primarily think about doing X-rays at the kilo electron volt range. And we've all been taught that as KVP increases, what decreases in terms of what's happening inside the patient? Excellent. Photoelectric effect goes into the crapper, right? As I turn the KVP up, I'm turning down the photoelectric interactions. And what predominates is Compton scatter now, right? Anytime we're taking a portal image at the mega electron volt range, we are not using photoelectric effect at all at that point, right? We're solely relying on Compton scatter to produce an image, right? We're solely relying on Compton scatter to produce an image. Why? Because the energy range is so high. There's no such thing as photoelectric effect at that high energy range. So all we're using is the differential absorption of Compton scatter. So you can imagine the image quality would suffer for that, right? So there's been a lot of evolutions in the development of how we're doing portal imaging, how we're taking radiation therapy pictures because of this very problem, right? But for us as X-ray techs, it's been ground into our brains that we need to use a lower KVP when at all possible, right? And so there's a tension there for us. How do I know that the KVP is low enough to reduce scatter, but high enough to penetrate through the patient and produce an image? Because if nothing gets through the patient, I also don't have a picture, right? So if too much is getting through, it's all scatter. If not enough is getting through, no picture. That, in a nutshell, is why we get paid the big bucks. But you might be wondering, well, what exactly is subject contrast? Well, I think a lot about the Supreme Court when I think about this. They had that classic definition of pornography. I know it when I see it, right? I know if it's art or if it's pornography when I see it. The same is true with subject contrast. I know it when I see it. It is a difficult thing to describe in so many words because of all the technical jargon that comes with it. But we definitely know it when we have it, right? And so of these two pictures, we can look at them and we can see that the picture on the left has better definition of all the anatomy on it. Now, granted, this is not the best image, so if it's not immediately popping out to you, I'm going to blame the projector for that. But on my screen, it's pretty clear, and if you're looking at this on your computer screen, it should be pretty clear. So let's talk a little bit about what we're seeing in this image that we're saying it has optimum subject contrast. Now, I'm going to define that term carefully. I didn't say it has high subject contrast, and I didn't say it has low subject contrast. I said it has optimum subject contrast, right? So what am I talking about? If the contrast is too low, sometimes that's helpful, right? There are moments when we want lower subject contrast. There's also moments when we want a higher subject contrast. It all depends on the differential absorption that's happening inside the patient, right? How much is happening inside the patient? So we'll talk a little bit more about that. But for right now, just know that I said optimum subject contrast. That means the appropriate amount of contrast to make a diagnosis. So I'm going to call optimum subject contrast the appropriate amount of contrast to make a diagnosis, or for radiation therapy's sake, the appropriate amount of contrast to guide treatment. Right? Can I see what I'm trying to do? In the world of pictures and photography, subject contrast and contrast is everything. Without contrast, you do not have a photograph. And so we can kind of make the same argument for us here. Without contrast, we don't have a picture. We don't have a diagnosis. We don't have a treatment plan. So this image on the left, you'll notice in terms of the overall whiteness and darkness of these images, they are essentially the same. How can I say that? Well, what I'm looking at first and foremost is the mediastinum, the shadow of the heart, right? Can I see a little bit of the T-spine through the mediastinum? I'm using that as my measure of whiteness on the image. It's the thickest part of this patient's anatomy that's on this image. It's a little difficult to see on this projection here, but the answer is yes. I can see a little bit of T-spine through the mediastinum on both images, right? So the overall degree of whiteness on these two images is the same. It might look that like one of them is more white than the other, but that is just an apparent difference, right? Now we can talk about the overall darkness on the image. For that, I'm going to look at a thinner part of the patient's anatomy. Why? Because I'm interested in what's happening in terms of differential absorption inside of the patient in an area that's less dense, right? And so I'll look at the lungs in this instance. A lot of times I'll look at the apices of the lungs, but in this case, they've got the clavicles up there, so it's not perfectly positioned in terms of marrows or whatever. But if I look somewhere in the lungs and try to identify one of the darker spots in the lungs, overall I would say the amount of darkness in the lungs is roughly the same, right? Maybe not perfectly so, but pretty close to each other in terms of the overall darkness in the lungs. There's clearly no place in the lungs that's completely burned out, right? Okay, so the overall lightness and darknesses of the images are the same. What differs between these two images is the amount of grays. Everything between the absolute whitest and the absolute darkest. So the amount of grays are different between these images, right? Interestingly enough, this picture on the right has less grays, right? Strike that. Sorry, it has more. I'm sorry. Slow down, sorry. Okay. It has more shades of gray in this picture on the right. Okay? All of those shades of gray are no longer helping me, right? Why? Because it is a lower contrast. It is difficult to see where a rib stops and the lungs start. Why? Because I'm seeing every gradation of gray between the ribs and the lungs, right? So there's low contrast now between the ribs and the lungs, right? I'm not able to differentiate between those two. The image on the right has a slightly higher contrast. Case in point is I can look at the difference between the ribs and the lungs. I can definitely tell what is rib and what is lung. I can see the lines between them. A better example might be I can see the lung markings more clearly. I can tell the difference between the lung markings and the lung tissue, just the open air space. What's that? The one on the left. I apologize. I apologize. Thank you for catching that. The one on your left. Yeah. I feel like the weatherman. I'm not particularly good at that, so thank you. But yes, on this image on the left here, we have a slightly higher contrast, right? And so we're able to see more clearly between what is ribs, what is lung markings or lung branchings, and what is just kind of open air sacs. So we're going to say that's an optimum amount of contrast. It allows us to make the diagnosis. It allows us to make the distinction between what is and what isn't supposed to be there. Well, the next question for us all should be, well, how do I get that optimum amount of subject contrast? And there's a big three, right? These are the things that if you're interested in tattooing something on your body, this is what you need to tattoo on your body. These three things: the tissue thickness, tissue density, and atomic number, right? Now, these things might seem pretty obvious at the first brush, but we need to carefully define what we're talking about here, right? So tissue thickness, what we're talking about is something that can only be measured with calipers, or in radiation therapy we used to use these separation calipers. And what we're measuring is the distance from, for example, if we're setting it for a breast treatment, the distance from this part of the treatment margin to this part of the treatment margin. Because we're going to be coming in at an angle to treat the patient's breast, because we want to avoid as much as possible hitting the lung or the heart, right? So we're going to set a margin on this side, on the lateral side, and a margin on the medial side. And everything measured between this line and this line is the separation. It's the area that we're actually going to be penetrating with the X-ray beam, with the treatment beam. The same thing we're doing in radiation, in X-ray, in diagnostic X-ray, when we use a caliper to calculate what's the part thickness, right? So it's the same calculation, and we're using it in a very similar way. It might look different, but it's being used in the same way to calculate how thick is this part, right? How physically thick is the tissue itself, right? And it's a measurement. We can say, okay, this patient's chest is roughly 20 centimeters thick versus the next patient's chest is 22 centimeters thick. Now that might seem like a really small difference, and it is. But we can all agree that it would have a difference in terms of what we had and what remains. It would impact subject contrast, right? And there's no way to gauge it with your eyes. That's worth repeating over and over and over again. There's no way to look at a patient. None of us, with a few exceptions, have ever worked at a carnival, right, guessing people's weights. And even those people who work at carnivals and guess weights, they can't tell you, well, how wide is my thigh, right? We lack that perception. We can kind of guesstimate distances, but we're not particularly good at it, is what I'm saying. So we need rulers, we need calipers, we need measuring tapes to know how thick something is, right? The reality is very few x-ray techs use calipers anymore, right? I'd be curious to know, in radiation therapy, are we still using calipers and ways to physically measure the patient's separations and stuff like that? Good. It is important. So that is thickness. That's the definition of thickness, is how much of a distance do the x-rays have to travel through the patient? Thickness. This is different from tissue density, right? This is different from tissue density. And the way that I would think about tissue density is how relatively solid or relatively fluid is the tissue, right? How relatively solid or how relatively fluid is the tissue. So in some ways we're talking about the tissue state. The reason I'm talking about it in that term is because of this experiment that I had that really freaked me out. Ice is less dense than water. The reason we know this is because ice floats on water, right? Ice floats on water. So we can easily prove that ice is less dense than water. Now, it would hurt more if you got hit in the head with ice versus if you got hit in the head with water, right? We all agree that it would hurt a lot more to get hit in the head with ice. In fact, I've seen people killed by getting hit in the head by icicles when I lived in Utah, right? Literally impaled on an icicle. That's how much it could hurt. But we've said that ice is less dense than water. So what's going on? Well, ice exists in a different state, right? It's in a solid state versus water is in a fluid state. So if things interact with us in a fluid state, they just splash and then they run off of us, right? That's what happens in a fluid state. It might be more dense, but we didn't really care. It didn't hurt us that much, right? Versus if something is in a solid state and it strikes us, it's going to cause trauma, right? So when we talk about tissue density, we are talking about that state as well. And the reason I'm stressing that is because if you take an x-ray picture of that cup of ice water, guess what? The ice will appear better on the x-ray than the water, right? So the simple rules of just saying it's less dense or more dense don't necessarily apply nice and neat. We have to consider its state as well. If you want another example of that, it kind of goes along with atomic numbers, so I'll come back to it in a minute. But just know for the purposes of our x-rays, when we're looking at an x-ray image, I can see bone. Why? Because it is denser. It's hard, right? I can see it's going to attenuate more. Why? Because it's denser, because it's more hard. It would hurt more to get hit in the head with a bone, right? I can see fat less. Why? Because it's less dense. It's in an almost fluid state, right? It has a lot of water in it. So it is less dense. It would not hurt so bad to get hit in the head with some fat. It'd be gross, but it wouldn't hurt. The x-rays are having the same kind of conversation as they're passing through the patient. Well, I just ran into this bone, it really hurt, stopped me cold, right? I just ran into this fat, went right through it. So that differential absorption process that we're talking about is happening inside the patient's body. If it strikes something that's solid, it's more likely to be stopped. If it strikes something that's more fluid, it's more likely to pass through it. Okay? Atomic number is the final thing, and this might be the one that trips students up the most sometimes, but we have to think about the periodic table. If it's high up on the periodic table, it's going to stop more X-rays. Why? Because it has more electrons to ionize. It's as simple as that. What we're talking about is ionizing radiation. Something with more electrons is more easily ionized, so it will ionize more, right? X-rays are going to interact with it more often. Now, interesting thing about our bodies is we don't have a lot of we're not made out of like radioactive materials, right? We're made out of carbon and oxygen and hydrogen and things like that. Pretty low on the periodic table. Pretty low on the periodic table. The rare exceptions for our bodies might be things like calcium. That's a little bit higher on the periodic table. So not only are bones more physically dense, right? They also have more calcium in them, so they're more likely to attenuate both because of their density and because of the higher atomic number, right? And that's one of the main reasons why we're able to do portal imaging right there, is just because of the bones. So it's a significant difference. Bones are going to be that much more apt to attenuate than other things because they're both physically more dense. It would hurt more to get hit in the head with a bone, and they have a higher atomic number than other things. Versus something like fat, which is mostly water molecules, right? That's hydrogen and oxygen, pretty low on the periodic table, right? So it's not going to attenuate as much stuff. That's the atomic number discussion. With a little parenthetical beside it, because we use this atomic number thing as a way to improve image contrast, right? And it works like this. You inject the patient with iodine. Why? Because iodine's really high on the periodic table. Like I think it's 53 or something. It's really up there, right? It has a lot of electrons. It's going to attenuate a lot of X-rays, right? So the iodine's going to show up real clear on this picture. Even a little bit of iodine would show up really clear on the picture. Barium, the same thing, right? Has a really high atomic number. Even though I can drink barium and it exists in a fluid state, right? It is very, very high on the atomic number. So it's going to attenuate a lot of X-rays. So those are the three things that affect subject contrast. And as the X-rays are passing through the patient, these are the types of interactions that are occurring that result in a difference between what we had and what remains, what actually is there to interact with the image receptor. Okay, well we've kind of danced around this point, so now let's talk about it directly. What are the effects of scatter on contrast? Well, we know it's not good, right? And scatter, when I'm talking about scatter, I'm talking about Compton effect, right? Those Compton interactions. As we increase KVP, what we've just established is that scatter increases as well. And if scatter increases as well, our contrast decreases. Contrast goes down. Right? What we're saying is that as KVP increases, scatter increases, and so contrast decreases. Contrast and scatter are enemies. Scatter hates you and wants to destroy you, right? Here's an example, a classic example from diagnostic imaging of a place where this is very apparent, right? The lateral L-spine. This is a very difficult image to get, right? Especially if you're trying to set a manual technique. Back in the day of film, this was the crown jewel of X-rays to nail. It was one of the hardest X-rays to get on a film system, and we'll talk about why that's the case in just a moment. But for film, you had to know your technique 100%, right? Because you're fighting that war on the film between scatter and useful x-ray. Now, for a lot of those x-ray tech students now, you're thinking, oh, lateral L-spine, that's not that hard. You just, set up at the right level and you get a good picture, right? But think about all the technology that you're applying to that image. You're using an automatic exposure control and you're using a grid, right? So those devices are helping you in a lot of ways, and we're going to talk about those devices here in just a minute. They're helpful for us as radiation therapists too. But on these two images, it's very clear that the image on our left has the better contrast, right? It is a more diagnostic image, so it has an optimum amount of contrast. Yes, the contrast is higher, right? But that's helpful because I'm not trying to look at soft tissues on this image. I'm trying to look at bones and evaluate for fracture. I'm trying to look at disc space and evaluate for whether or not the disc is ruptured, right? So of the two, the one on the left has the better contrast. What is accounting for the differences in the contrast between these two images? It is scatter, right? So if we were to take a flying leap at which one of these was potentially produced at a higher KEV, at a higher KVP, we would need to say it's the image on the right, correct? Because the higher KVP would produce more scatter. But if you're feeling a tension as I'm talking about that, and if you're tracking with me, there's a tension there because we need enough KVP to get through the patient. And we know that we're all really thick right in this area right here, and that the bones of the lumbar spine are also super thick because they have to support everything from, from here up, right? So it's very, very dense. It's physically thick, right? We put our caliper measure on there. So all of the things that are there to increase attenuation are brought to bear here, right, on this image. And if we turn our KVP up too high, we're just increasing scatter. So we can blame the patient is what I'm saying. Blame the patient. What affects subject contrast? Largely it's variations in patient anatomy, right? And that again is reason two we get paid the big bucks. It's because God did not make us all the same. We are at every possible range of thicknesses and densities and atomic numbers. We are very diverse on all those three things that we've defined, right? Very, very diverse. And so those diverse differences require different techniques, right? Because they affect scatter. So I'm just going to recap that. Here's a fancier drawing of the exact same thing that I was kind of whiteboarding over there. And this has got it all in the fancy mathematical way of talking about it. And the one thing I'm going to add to the conversation at this point is something that we've kind of talked about a little bit here, but it has to do with exposure latitude. Exposure latitude. So exposure latitude is a question, you'll probably have it on your registry for both therapy and x-ray. Anytime I think about exposure latitude, I'm kind of thinking about this chart in the back of my mind. That's why I've given you all this information. But our textbook defines exposure latitude as the margin for error in setting a technique that the system will allow. It's your margin for error in technique. The margin for error in technique that a system will allow. And so if we go back to the discussion about the lateral lumbar spine, I was saying that for the days of film, there was a narrower latitude. You really need to know your technique well to get a lateral L-spine on film. Why? Because the system had a narrow exposure latitude. You were pushing the threshold of what your system could do. With digital, if this is our film exposure latitude between my two hands right now, digital's latitude roughly extends from my hand to the wall. It has a very wide exposure latitude, a hugely wide exposure latitude, right? And that huge exposure latitude is the reason why we have this class. It's the reason why we've had the evolutions in portal imaging. And honestly, if we're really honest as X-ray techs, it's the reason why we're exposing our patients more, right? Because the height of the exposure latitude extends off into that direction where KVP has gone under the Compton line, right? And so we're able to expose people more and more and more and still get a pretty picture. Why? Because digital systems have a really wide exposure latitude. They have a wide margin of error, right? So for any of you who've ever been lectured by an old school X-ray tech about, well, back in the day of film, we had to really know what we were doing or whatever, they're right. They're right. And you can just kind of say, I understand, you're correct. You had a much narrower exposure latitude that you're working with, and now we have this super wide exposure latitude. And chances are, if you put it to them like that, they'll be like, okay, this person at least knows what I'm talking about. So just to review, and to put it in really nerdy mathematical terms, right, that you might need to know, X-ray techs, you might need to know this. Photoelectric effect is inversely proportional to the cube of KVP. What does that mean? It means it is exponentially going to fall off. When you see inversely proportional to the cube, just know it's going to plummet, right? So that's what we see it doing here on this graphic. The two lines that represent KVP are these ones that are falling off really quickly. The differences between them that you can see are the difference between tissue and bone. But it falls off real quickly. That's what inversely proportional to the cube means. Compton effect is only slightly affected by KVP. So here again we see that Compton effect kind of meandering along in a pretty straight line, not just kind of fat, dumb, and happy, not really much is changing with it. So as KVP increases, Compton effect becomes the predominant interaction. That means that percentage-wise, it's more likely to happen. Percentage-wise, it's more likely to happen, which is what we've just been kind of talking about quite a bit. So this comes to one of those golden nuggets of X-ray technology that stumps every junior student, right? And they rack their brains against the wall trying to figure this one out. But the reality is to increase subject contrast, we decrease KVP. It took me months to figure that out as a student. That made no sense to me, right? But it's one of those weird things that we've come to understand through the science, that if we want to increase our subject contrast, we need to decrease our KVP, right? Now, if you want to know what's the part of the conversation that we're really dancing around with all of this, it's patient dose, right? I've not said anything about patient dose. But if you think with me for just a second, we can take this to the next level. I've just said to increase subject contrast, decrease KVP. Yeah, and it would increase the mass. So I've also increased the patient dose. I've increased the patient dose. Even without increasing the mass, I would have marginally increased patient dose. Why? Because there's that many more photons getting trapped inside the patient, basically. All of them are hitting in the patient, they're hitting a Bragg peak, and they're releasing all their energy in that Bragg peak. Okay? That's what we're talking about. All right, well, since scatter is the enemy and we hate scatter and scatter hates us, what are we going to do to fix scatter? And this is very, very important for us as X-ray techs and as therapists. Super, super helpful. This is a key part of how conventional simulation works. We're going to use a grid, right? We're not going to be able to fix the scatter on the front end, is what we're saying. We're going to fix it on the back end. We can't fix it on the front end. We're going to fix it on the back end. And if you're wondering what I'm talking about when I talk about a grid, I'm talking about this very terrible drawing here. So here again, we have the X-ray tube. We have the primary beam incident on the patient. Here's our patient in a transaxial view. And then we have that tiny space right there where subject contrast lives, right, in the secondary beam. And then we have this grid, and it's doing something, right? What is the grid doing? The grid is allowing the photons that have the same trajectory across, the same straight trajectory, it's allowing them to go through. So it's saying, okay, you came directly from the tube, right through the patient, you can come through, you're good, right? But those ones that got a little bit drunk, right? They had a Compton effect, they made a mistake, they just turned 21. They made a mistake inside the patient, they went off at a funny angle, it's stopping them, right? So this is like the DUI screening at Beale Street at 2 o'clock in the morning, right? It is looking for the ones that are driving funny, and it's pulling them over. It's saying, stop, you're not getting through. Those ones that are driving funny are the ones that were Compton affected in the direction of the image receptor. So we said that Compton effect happens in all directions. In fact, it's our primary form of occupational dose is Compton effect coming off the patient. Backscatter radiation. The stuff that's being backscattered back towards the tube, I don't give a crap about because it's not going anywhere close to my image receptor. But those nasty ones that scattered inside the patient and then we're going to try to interact with my image receptor, nuh-uh, I'm not playing that game. So the grid stops that cold. How does the grid do it? Well, that's what we're talking about when we talk about this grid ratio stuff over here. The way grid ratio works is you have a height, which is the distance or thickness of the grid. If I was actually holding the grid, it would just look a lot like this folder here or something. It would just be a piece of metal, right? But inside that metal, I'm saying the height of it is how high it is in this direction, right? How much the x-rays have to get through it, right? So I'm calling that the height. It doesn't really seem like the height, but that's what I'm calling the height. So this illustration here is an illustration of the grid as though I've cut it right here and I'm looking at the insides of it. So the height is that distance the x-rays have to go across. The distance is the distance between interspace materials, right? So what we're seeing inside this grid, the black lines here are lead. They're lead because lead is super dense, right? This interspace material is just some kind of stuff like carbon or something that x-rays can get through easily, right? It's something that's not going to stop very much x-rays. So that's this interspace material here. So lead, interspace, lead, interspace. And if I have an x-ray that's coming straight down from the x-ray tube, it's just going to pass right through the interspace. And I mean, this stuff is super thin. So don't worry about whether or not it hits the lead. It can't. Let's just say it can't hit the lead. It's just going to go straight through, right? But if it's one of those Compton effect ones and it's scattered in a funny direction, it will hit the lead and it will get stopped. So it will not make it over here to the image receptor. You can think about it as being like a filter. It filters out the bad x-rays, the Compton effect x-rays. So we can still use a high KVP to get through the patient's anatomy for the lumbar spine, but we're going to clean up all the scatter on the back end. We're going to get rid of it as it's exiting the patient. So we need to know that. That is helpful for conventional simulation. There is a grid that's used by the fluoroscope, and it is used to clean up scatter and to get us a prettier picture. The problem with grids, though, and this is kind of goes back to what Ms. Rochelle was saying, is anytime we use a grid, we have to use a higher mass. Why? Because we're getting rid of x-rays. We're getting rid of x-rays, and so to make any kind of picture, we're going to need to increase our mass. And we have to increase it a lot. Like if you want to increase your patient dose, the number one easiest way to do that is use a grid. So this makes a really strong case for how important optimum contrast is. That we are willing to increase patient dose in order to have better contrast, right? By using a grid. So anytime we're throwing a grid on an image, we are significantly increasing patient dose, but we're doing it so that we can get a good diagnosis. We're not just doing it willy-nilly. The rule of thumb for X-ray text is that grids should only be used in the event that the anatomy is 13 centimeters or thicker, right? I don't think that's on the registry or anything like that, but just know that there are some things we should use grids for and there's some things that we just shouldn't because they're too thin, right? They're not thick enough, to go back to that earlier slide. Anytime we use a grid on your PowerPoint slide, it has the types of dose increases that we would expect to see. And also on this slide, we should have the grid factor, right? I don't think it has it on there for you. But the way that I generally look at grid factor is I just go down this list of grids and I put, for no grid, a grid factor of 1. For a 5 by 1 grid, a grid factor of 2. And then 3, 4, 5, on down the list, right? That will get you pretty close to where you need to be. So if we're changing from a grid to having a grid to not using a grid or whatever, we have to divide out some stuff. And we can drill down more into that in Symposium on Friday. But just know that we do have to increase, just to go from no grid to having a 5 by 1 grid, we've just doubled the patient's dose. We've had to increase mass enough to double the patient's dose. Let me say a few things here from the textbook about grid usage. So grids are our friends, but they do make for some problems from a digital imaging point of view, right? And this is in the subsection, use of grids with digital radiography. One of the first problems that we can encounter anytime we're using a grid, and this is kind of grid 101 type stuff, is if there's any kind of tilt in the grid, right? Chances are we could close off the grid interspaces, right? And the way that I think about it is like closing blinds. If I've got the grid untilted, the blinds are open, right? But if I start to tilt the grid, I'm closing the blinds, right? And there's going to be x-rays that are actually helpful x-rays that are now going to get caught by the grid. For radiation therapy, you don't have to worry about that because you're using a grid on a fluoroscope and you cannot tilt it. It's affixed to the image receptor and it's not going to tilt. For our purposes in x-ray, this is a potential because we do portable film. And anytime we're doing a portable on a patient slouched over in the bed, it's very easy to angle the grid and to cause that kind of grid cutoff is what we call it, or a grid artifact. We can also imagine it'd be wrong if we flip this thing upside down, which is generally very difficult to do, but that can also cut things off. If we use the grid inappropriately, it can cut things off. But for digital, you can use the grid perfectly fine and still wind up with an artifact. You can use the grid perfectly well and still wind up with an artifact. This is especially true for computed radiography. So what's happening? Well, you may remember our brief conversation about the Nyquist theorem, that we have to be sampling twice in order to have a good image, right? We have to sample twice for any one pixel. With grids, though, we've cut off our sample, right? We've decreased our sample size. And so we can start to affect that Nyquist theorem. Additionally, if we're using a computed radiography cassette and we're scanning it with a laser, if there's areas where the laser's scanning over and it's scanning along the fans of the grid lines, it will detect that. And it's going to throw that laser off, right? If it's scanning in this direction, it's probably fine. But if it's scanning in this direction, it's going to detect it. So we're going to call that an aliasing error or a Moiré artifact. We've talked a little bit about the Moiré artifact. It was the picture with the windows, and the windows looked weird, right? Imagine the same thing can happen now with the grid lines. The grid lines could look weird, right? So the Moiré artifact is an interference pattern. and it's a false presentation of actual lines. So the lines would appear weird when they weren't supposed to appear at all. So as a general rule of thumb, if we're off on portables, we should not use a grid higher than a 6x1 grid. So you'll notice most of your grids, if you were working on a portable machine, 5x1, 6x1 max for any kind of stationary grid, something that's not a bucky, that doesn't vibrate as you're taking an image. So stationary grids, 6x1 is the maximum grid. And you know what, that's helpful? That's helpful because even though we're kind of down a rabbit trail now, it's helpful because we know how best to use grids for portables, and we also can anticipate there won't be too many wackadoodle questions about grids on the registry, because we've just limited the number of grids usable to 2 for mobile. I think that's all I need to say about grids. We'll come back to grids here in just a moment because digital does offer some solutions for grids, right? And so that'll be one of the last things we'll talk about today. Oh, so does your presentation have the problems with grids discussion on it? It does not. I didn't upload that. Okay, I'm sorry. Check back. Pretty much everything that I just said has a PowerPoint slide for it, and I will upload it. But it's just talking. It just offers you some illustrations of what the aliasing artifact looks like, and it talks a little bit more about grid factors. It shows you a radiograph in which there's a grid error. Okay, so my apologies for not uploading that. Okay, what about the AEC? So AEC is short speak for automatic exposure control. It is our friend. And if we were to go back to our discussion of the lateral L-spine, the AEC, I said, is one of the tools that we're using now to take better lateral L-spine images, right? So what an automatic exposure control is it's this device here on the right. It looks like a targeting system of some kind, right? And each one of those targets there towards the center, the 2 circles and the rectangle, are radiolucent, the x-rays can see through them, ion chambers, right? So here's one of the reasons why x-ray techs need to know how Geiger counters work, right? Why? Because you use a Geiger counter, something very similar to a Geiger counter, with every picture you ever take with an automatic exposure control. You are basing your technique off of the amount of ionizations occurring inside of an ion chamber. You're basing your technique off of the amount of ionizations that occur inside of an ionization chamber, and once you reach the appropriate amount of ionizations, the technique cuts off. The image is taken. For the purposes of digital, that's great. That's really, really good. Super helpful. And in fact, it is a big part of how imaging works in radiation therapy, all using the exact same principles to acquire your images, right? You're measuring the number of ionizations that are occurring, and you're saying, okay, we should have a picture now. Anytime we do a portable image. So this automatic exposure control is good. It has applications outside of X-ray technology. We use something very similar to it in CT. It's called automatic dose modulation. But if we don't line the patient up right, we've got a problem, right? And it's surprisingly easy to line the patient up wrong when we're using an automatic exposure control. So back to the lumbar spine issue, the lateral lumbar spine. The lateral lumbar spine is kind of more towards the patient's back, but sometimes it's difficult to gauge exactly where it's at because it has this curvature to it, right? It has a lordotic curvature to it. So it kind of sways forward. And it can sway forward more or less on different patients, right? So if I don't have that lumbar spine inside of this ionization chamber where I'm counting how much ionization occurred, I can either overly expose it or underexpose the image, right? It's very easy to do either if I don't have it lined up correctly. So, the first rule of using an AEC is don't do what this technologist did here on this decubitus view. They activated the automatic exposure control. They either selected the wrong panels or the patients just misaligned so that they got it looks like a underexposure, overexposure. I can't tell exactly what's going on here, but the automatic exposure control probably continued to expose because it hadn't yet gotten all the ionizations that it wanted, right? So we have this burned out lungs, a whole lot of scatter inside of the abdomen, which is exactly what we don't want on this image. The other thing to do is if you take an image using the AEC and it appears underexposed, it could very well be that it did not receive sufficient signal. It cut off too soon, right? So image model would result from that. So it thought it had enough ionization. It didn't. It was too grainy. In that case, increase the KVP. That's just a general rule of thumb. If you're using an AEC, if you're like, oh my goodness, this picture looks like crap, I don't know what the AEC did, increase your KVP, repeat the image. And just to reiterate, anytime we're using AECs on either CR or DR systems, make sure that you're aligned appropriately. Okay. So I mentioned that I would come back to grids very briefly. These are two images that were produced by Fuji. I think it's on their DR system. And they used a virtual grid to clean up the pictures, right? So it did not require increased technique to the patient. They're using the software to clean up the picture, right? That's what a virtual grid means. So he talks a little bit about how virtual grids work in this chapter. I do think it's interesting and helpful for us to know because this is something that's on the horizon and it'll soon be here for us all. It estimates amount and angle of scatter. It estimates the amount and angle of scatter given the beam profile. So in other words, it does a dosimetry calculation. It does a dosimetry calculation. And it also calculates for the grid effect. It calculates how much would I expect the grid to interact with that scatter, right? So now it has an idea of how much scatter should there be, how much should the grid interact with that scatter, and then finally it does a granularity improvement, right? So it applies a filter to it. To go back to our discussion of makeup, right? It looks at the picture of the person that it's trying to clean up, right? It says, how many pimples need to be covered here, right? How much will my concealer cover up the pimples? And then it covers up the pimples, right? So that's essentially how virtual grids work. They're doing it on that image data, though. They don't require increased technique. They're cleaning up the image data based on what it expected. So that's a powerful piece of technology, and I expect to see it increase as well. Thank y'all.